Thank you. First of all, I would like to thank the organisers for asking me to speak here. So this is kind of a survey talk. I want to discuss this story from quite a distance.
On your previous slide, your type number is not complete.
Yeah, so I only have one paper in March 2017, and it's this one. So if you go to the archive with my name, you'll find the... there's also, I taught a course, and there's the start of a project for some course notes as well. So the paper here is a paper that was for Hitchin's birthday, which is like a survey, but it was restricted to be 21 pages, and so it's quite sharp. It's more a sort of a list of the references to the stories. There's more sort of explanations in these course notes, which I'm planning to expand. And so probably more of the details would appear there. So the aim is a bit to explain the language that I've been looking for to try to express what we do. So I came here to a talk of Manin in like 20 years ago, and I sat there, and he spent like the first half an hour explaining the definition of a graph and sort of talking about the importance of having the right language. And at the time I thought this was crazy, but the problem is that you don't really understand that you don't necessarily have the right language in which to express things. And so part of the purpose of the talk is try to explain some possibly useful or better language to describe what we're doing. The basic aim at the start was trying to understand geometrically what are the 6 Painlevé equations. So the motivation for this, so people like Maxime would have a particular solution to a particular Painlevé equation, and then take an expansion of it, and they'll say, well, the numbers which occur are extremely interesting, and they're counting the rational curves in P2, or some such story. And it begged the question to give a geometric picture, a clean geometric picture of what the Painlevé equations are. So you can look at the list on Wikipedia, but they're basically a deformation of the theory of elliptic functions. So for instance, if you look at Painlevé 1, you get this sort of innocuous differential equation, which is plus t. So Painlevé found these with the alpha method, which basically means that you can put in a parameter and take a limit that becomes something that also has the Painlevé property but is simpler. And so here it's possible to put in a parameter to get to y double prime is 6y squared, and then it's possible to solve this in terms of elliptic functions. And so it's easy to integrate this to get y prime squared is 4y cubed, and then this is easy to solve as it's a particular case of the equation for the Weierstrass P. And so that was the first perspective, and then there was a different perspective that came from Richard Fuchs, who said that the Painlevé equations are the isomonodromy deformation equations. So in particular for Painlevé 6, it's the equation that arises from looking at families of 4 punctured spheres. You're basically doing non-linear gauge theory on a 4 punctured sphere. And there's it's probably the first example of a non-linear differential equation, which is best understood as controlling the deformation of a connection on a vector bundle. So Poincaré said that the work of Painlevé looks as if it's in a different ocean. It's an île originale in a neighboring ocean. And I think the reason was that Painlevé was doing non-abelian gauge theory back in 1900. So in looking for the language which to describe this, you read the papers of Simpson, and he has all this business about the non-abelian Gauss-Manning connection for an arbitrary family of smooth projective varieties. And so it becomes clear that the Painlevé 6 story is the version of that for a 4-punctured sphere, looking at the logarithmic connections there, the tame picture. And this gauge theory perspective of Richard Fuchs was extended by Garnier to explain the other 6 Painlevé equations as the isomonodromy equations for the irregular equations which occur by coalescing these 4 poles in this 4-punctured sphere. So for instance, Painlevé 1 would occur by looking at a particular connection having a pole of order 4, as I imagine most of the people here know quite well. But it begs the question, to understand better the extension of Riemann-Hilbert. So in the tame case related to panel of A6, you're looking at the monodromy map between a 4-punctured sphere and the space of representations of the fundamental group. To explain the other 5 panel of A equations in the same way, you need to use the irregular version of that, first looked at by Birkhoff. And so the question that is being asked is, why do we not know the story of the Stokes data as cleanly or as clearly as we do the story of the representations of the fundamental group? And I think the answer is basically because it's been dominated by algebraic geometric people who aren't particularly interested in integrable systems and panel of A equations. And there was an opportunity to do some work to explain more intrinsically what the Riemann-Hilbert-Birkhoff correspondence on curves is all about. And in particular to understand the 6 panel of A equations and their higher order versions better. Okay, so that's the basic questions. So for instance, I then made the connection with this work of Simpson in my first paper, and I've spent a long time since then generalizing it from the generic case for GLN to other reductive groups and to the non-generic case for arbitrary order poles, and I hope to mention that. So because the talk is quite complicated, let me just state a result at the start. Perhaps the main algebraic statement is this, that you have this standard picture that you have a complex reductive group like GLNC, and there's a way to associate a Riemann surface to the character variety or the Betti moduli space there, and it's the quotient of an affine variety, the representation variety, the space of representations of the fundamental group, by the conjugation action of G. And then you can explain the Weil version the same type of way. You can work out what to fix at the poles. You fix an irregular class. You have to define precisely what that is. And that will give you a space also. And it's possible to describe it in such a way that it too is the quotient of an affine variety, the Weil representation variety, the space of Stokes representations of this Weil surface groupoid pi, again by a reductive group H. So basically it's slightly different because there's this breaking of structure group at the poles. The formal local system is a graded local system, and the group gets reduced from G to a subgroup H at each of the poles. And you look at the product of those over each of the marked points. So that's possible to define, and you can read the papers of Ramis and Ekal and others how to do that, and you change it a bit in order to describe it in the way as a quotient of an affine variety by a reductive group. And then you can prove the results that people know and love upstairs in this sort of generalized context also, that this Betti space, the Weil character variety, is an algebraic Poisson variety, and the points of it are the reductive Stokes representations. So each of these Stokes representations has a differential Galois group attached to it. And in the tame picture at the top here, you're just looking at the space of representations of the fundamental group. It's known that the differential Galois group is the Zariski closure of the image of the representation. And that has a generalization, the Ramis-Schlesinger density theorem, that defines the differential Galois group also in the Wild picture. And the points of the variety, the closed H orbits, are the ones whose differential Galois group is a linearly reductive group. So it's a possibly disconnected group whose identity component is reductive. So that's the exact analog of the results at the top.
So Philip, the top one doesn't really need a Riemann surface, right? It just needs pi1 of the surface.
So if you look at my notes, I carefully explain this subtle point about the choice of generating loops. If you just choose, like, genus and the number of the punches, then you have an abstract group there. But all of this isomonodromy business is in that choice and identification between the abstract group and the fundamental group of the surface. If you vary the surface, that's where all of the isomonodromy systems occur, and the panel of A equations are just the Durand version of that. So yes.
But my point was just that there's an underlying sort of independent description of this that just depends on the smooth structure of the surface. But is there such a thing for the second one, the Weil characters?
I can give you a purely topological description of what the space is. But yeah, I think we're more looking at holomorphic deformations of surfaces which are holomorphic. And the last thing is if we look at
this theorem, if I understand correctly, that it's part of the theorem is the definitionless varieties, because somehow you only define them as a set, but to say that the variety, because when writing as a quotient, so you have to explain what you mean by quotient.
So this is the affine GIT quotient. I'm looking at the variety associated to the ring of H invariant functions, and that's what I mean by the points. So I'd like to use the double slash to be the multiplicative holomorphic symplectic quotient. So yeah, that's just a question of notation. And the point at the bottom, if you have an arbitrary admissible family of these Weil surfaces and look at the corresponding Betti spaces over there, those form a local system of Poisson varieties. So basically, the differential geometric perspective would be a bundle with a complete flat nonlinear Erasmus connection. And that's kind of what the panel of A equations are, and that's sort of a universal statement. So I gave the references for this in the abstract. So basically this last part is put on the archive in January, and the rest, I mean, the main statement with Daisuke was on the archive in 2015, and that's a sequence of papers that goes back to this first quasi-Hamiltonian paper in 2002. And we have this sort of sequence of 4 papers which generalizes that. Okay, so let me back up a bit and try to explain the title of the talk. So one has the exponential map. If I have a complex Lie group, I can look at the Lie algebra over on the left and the Lie group on the right. And you have the exponential map, which is a map from the Lie algebra to the Lie group. And it's a trivial remark that that's just taking the monodromy of a very simple logarithmic connection on a disk. I have this connection having a first order pole, and so on the punctured disk I just have a holomorphic connection. I take a base point in the monodromy of that, and that will give me the exponential map. But once I phrase it in that way, it's clear that this map has lots of generalizations. If I replace this rational matrix of one forms by an arbitrary rational matrix of one forms like this, one might hope to have a massive extension of this picture. So we look at connections with arbitrary poles, meromorphic connections here, and lots of people have done lots of work to define what is the monodromy and Stokes data of an arbitrary algebraic connection on an arbitrary smooth algebraic curve. So in particular here I'm looking at the case of punctured spheres. The real question is it possible to cook up spaces and fix the orders of the poles and some structures at the poles so we get spaces of the same dimension on both sides? And Birkhoff understood that this was true in the generic case where you have each pole has distinct eigenvalues and then you have to be off of these real walls as well. So the fact is that we do know what to pick. I'll come to the definition of very good and good connections in a moment. So we get lots of generalizations of this map at the top of having 2 spaces of the same dimension, the additive space, the space of coefficients, and some type of multiplicative space. And in the tame picture of the first order poles, we would just end up looking at the space of representations of the fundamental group, and the Stokes story tells you how to extend that to get the right dimension spaces in general. And this goes back to Birkhoff in 1913 in this generic picture. So we can look at like isomorphism classes of these. So here we're looking at connections on the trivial principal G bundle or the trivial vector bundle. And you can quotient by automorphisms to go to moduli spaces. There's this sort of simple naive or additive moduli space M star over here. And this maps this wild Betti space on the right.
So it's Riemann Hilbert on the level of stacks objects. Yeah?
Riemann Hilbert Birkhoff, I'm more doing the moduli space version, but you could do the stack version also. The fact that you have something on the representation spaces really means that it works with the stacks as well. But yeah, that should be done carefully by someone. But I don't think that's particularly hard. So in my advances in math paper, I did slightly more. I mean, this in the generic case, there's a paper of Jimbo and Ueno who basically has this picture for generic connections, and I rephrase it in a slightly more modular way, but I also prove that it factorizes to an injective algebraic map to some Dirham space there, where you're allowed connections on non-trivial vector bundles as well, and then you prove there's a bijective correspondence with this extended moduli space here to some precise space of Betty data, which in the generic picture is precisely what was in the paper of Jimbo and Ueno. So you get this slightly richer picture, and then you understand what Hitchin and people have done with representations of the fundamental group, and there's this natural question of having a more analytic picture. Can you get Hermitian metrics into the story as well? So I wrote a letter to Olivier Bicard in 1998 that surely he would know how to prove this, and so he did, and there's a paper. So at the end of the day, you get this analytic moduli space. These are the solutions of Hitchin's equations. The equations were known before, both as the two-dimensional reduction of the self-dual Yang-Mills equation in dimension 4, or as these harmonic maps from a surface into here the Hermitian, the positive definite Hermitian matrices. But Hitchin kind of put this together and put it on a higher genus surface and proved that one can classify solutions of these in terms of the representations of the fundamental group. But it turns out if you go back to the original case of R2, there's still this story with complete hyperkähler manifolds as well. And so there's a classification of these Weil's harmonic bundles in terms of meromorphic connections or in terms of meromorphic Higgs bundles, both of which are purely holomorphic or algebraic moduli problems. And there's this third description in terms of Stokes data as well. So you have these three algebraic structures, just as in the case of compact surfaces that was looked at before.
Sorry, when you define this M-dual space, what is the actual definition? Do you also define some common sense?
I have a slide that has the definition of a very good and a good connection. You have to have a parabolic structure as well, and people think that if you have a parabolic structure, the connection has to be tame, and this is wrong. So we'll get to that. So when I've given this talk before, I would now switch. Well, we have this definition. We'd like to classify these incredibly rich geometric objects. So there's a story that there's a large class of these spaces M star, which are on the nose isomorphic to a Nakajima quiver space. And in the Pan-Lavey situations, this often gives the Okamoto-Weil group. So we want to use that graph or quiver to classify this whole package. The non-abelian Hodge space is this four tuple of spaces. It's a hyperkähler manifold with this triple of preferred algebraic structures, and we would like to classify them. In higher genus, it seems to be easy. There's sort of a Torelli result, I think. But in genus 0, there's lots of isomorphisms between them, and even between ones with different group as well.
M star is always connections on the trivial bundle.
Yes, in this story. So rather than that, I'll back up and explain a bit more of the story, because maybe it's not said very often. So I was basically interested in this rational differential operators in the middle here, and I was interested in the isomonogamy deformations of those. And it's known, so that's basically the space M star in genus 0, and then there's the Stokes picture over here. And these have this autonomous limit, which gives you the lax representations. So there's lots of sort of modular integrable systems which are known to be the flows of these lax equations for polynomial or rational matrices. And so Hitchin kind of extended this theory by saying, well, we can take the base curve to be arbitrary genus. And he has this theory of Higgs bundles on an arbitrary compact surface. And there's the non-abelian Hodge and Riemann-Hilbert there. Riemann-Hilbert in the compact case is kind of easy, and so that part is often swept under the carpet, but there is a definition of a holomorphic connection. And then one can put these two pictures together. Basically, there's lots of applications at the top that I wanted to understand better. In particular, the autonomous limits of the Pan-Lavey equations occurred in this Seiberg and Witten work. Their solution to this SU2 n equals 2 Yang-Mills involves 5 of the Panelet, the autonomous version of the Panelet spaces. And it's interesting to understand better the hypercalometrics which are there. So there's work of Boalch and Markman that looks at the Poisson structures on these modular spaces of meromorphic Higgs bundles. So the initial aim was to understand the Poisson or symplectic structure in the middle here, to put those together and then get the hypercalometric and the intrinsic definition of what the data is over here. It has various different perspectives, like Stokes local systems, or Stokes filtered local systems, or Stokes graded local systems. But if you look at the talk I gave here in 2019, I'll explain that. But there's also a paper, the topology of the Stokes phenomenon, that tries to spell out that clearly. So this is just a repeat of the story in the red box at the top. The main map, so that you have this analytic space with the Hermitian metrics, and then there are these two projections for getting the metric, either to meromorphic Higgs bundles or meromorphic connections, and you can prove that the polystable or the stable objects are the image of that and have a correspondence. I think I have a clear statement in a minute. So this autonomous limit is perhaps not so well known outside the experts in Panelet equations. So in 1919, so Panelet had understood the limits to the sort of families of elliptic curves, and Garnier in 1919 did the same thing, but for the Schlesinger system, and got this autonomous integrable system, which he integrated by inventing spectral curves. So this is the Schlesinger equations, I think, at the top. So you've got the times are all on both sides, and then he put in these parameters and scaled, and he ended up with something with the times being replaced by constants here. So this is now actually the first example of a lax pair. So it can be written in this way. If you scale by multiplying by a polynomial, you get this lax equation there. And he solved that the coefficients of the spectral curve are constant, and he solved this by looking at the flows on the Jacobian of this curve. And this is now known as the classical Goldman model, and all the Hitchin business is the higher genus analog, and you can sort of put them together to have the higher genus with the poles as well. So this story was rediscovered in the soliton papers. So for example, there's this paper of Adler and Bourbaki in 1980, who looks at the polynomial picture, and they say it was also done by Dubrovin, Matveyev and Novikov around the same time as well. And there's papers of Riemann, Semenov, Shansky, and a number of other people at the time. And then they figured out, there was this paper of Flashker and Newell that points out, well, actually it's in this paper of Garnier. And so there's a section in one of the most well-known isomonogamy papers has a section which explains this work of Garnier. And there's a paper of Chudnovsky as well, amongst others, which explains the link back to Garnier too. So I hope that's not too controversial, but I sort of feel as if people don't know the isomonogamy story so well. Okay, so let's change tack and talk about the moduli problem. So these are the holomorphic moduli problems that come out of this analytic picture. This is in this paper with Bickard, and there's some expositions on the archive. So the name is probably quite recent, but the actual, it comes from the models in this paper, I guess was on the archive in 2001. So you have a compact surface with some marked points, a vector bundle on the compact curve, you have a parabolic filtration at each of the marked points. And then you look at meromorphic connections with arbitrary order poles, and then you put in a condition about the compatibility between the filtrations and the irregular part of the connection. So basically the condition can be phrased like this. At each pole there's a local trivialization that splits the parabolic filtration, and such that you can write the connection in the form like, so A is dq plus something logarithmic, so there's the residue plus the holomorphic part, and the q part is the irregular type, which has to be diagonal. So it only has to be diagonalizable, but I'm saying that there has to be a basis such that it is diagonal. So basically it's a polynomial in 1 over z that has these diagonal matrix coefficients. And there's a further condition on the residue that it has to commute with all the coefficients of the irregular type, so it's in this block diagonal subgroup H, and it has to preserve the flag. So that's the definition of very good, and you can do slightly more if you look at these cyclic pullbacks as well. All of the analytic story works the same, so you can define a connection to be good if there's some finite cyclic pullback at each pole under which it becomes very good. This is the twisted case. And so you can look at moduli spaces of these. So you fix the irregular type, the associated gradient of the residue, and the parabolic weights. So you can do the same definition for the Higgs picture. And there's a table, so basically there's an extension of the paper. So Simpson looks at this in the tame case, basically Q equal to 0 in his JAMS paper in 1990, and the rotation between the eigenvalues of the residue and the weights is the same as in his table. It's a basic sort of story of how this hyperkähler rotation works from the Durand to the Higgs picture. So there's a slightly more intrinsic way to do it. If you read all of the papers on meromorphic connections, you'll see that there is a known statement about that there's a very clean way to give the formal classification of connections. And the nice way to say it that's due to Deligne is that if you look at the connections on vector bundles on the formal punctured disk, so you're allowed to arbitrary formal gauge transformations, then these match up with the I-graded local systems of vector spaces on the circle of directions. So it's a purely topological picture on the right over here. It's as if this is the statement for Riemann-Hilbert for formal connections. And this explains all of this breaking of structure group because the formal classification is in terms of these graded local systems. You have this circle of directions, this partial, this del, and then there's a covering space of that, so an infinite number of circles. I like to call them the Stokes circles. And you're looking at things which are graded by this covering. So most of the circles will grade the trivial vector space, but there's a finite number of circles which occur, and these make up the irregular class. So the Stokes circles are just defined by, it's basically the Stokes circle are the exponential factors which occur. So solutions have like e to the q in them, and you can look at Stokes's paper in 1857 and you'll see that there's e to the 2x to the 3 over 2 or something there, and that will be the Stokes circle which occurs. So an I-graded local system on the circle, it's just a vector bundle with flat connection. It has to be graded by a finite number of the circles. There's a direct sum decomposition, and these have to have monodromy which matches with the monodromy of the cover. So this is the same, if you think about it, as having a local system on this exponential local system, which is of rank 0 on all but a finite number of components. So you just have a finite number of these Stokes circles, each with a finite rank sort of vector bundle with flat connection. And if you take the ranks of those, that will give you the irregular class, these ni here. So you basically choose a finite number of Stokes circles, each with a multiplicity greater or equal to 1. That's the basic sort of extra data which you want to deform, and turns out to behave like the moduli of the surface, leading to this notion of Weil Riemann surface. You can also look at the conjugacy classes and eventually the weighted conjugacy classes if you have the parabolic structures as are. So it's easy to draw pictures of what these Stokes circles look like. They're basically covering circles with germs of equivalence classes of functions on them. For instance, if you look at the circle x to the 17, where x is the inverse of a coordinate at the infinite point. So here's a Stokes circle is infinity on the x-plane. It wiggles around, and you can talk about the points of maximal decay and things like that. So there's a picture of the projection of the Stokes circle x to the 17. So if you look in Stokes's paper, he actually draws the projection of the Stokes circle for Airy. So this is this 2x to the 3 over 2. And he draws this projection in order to show the growth and decay of this function e to the 2x to the 3 over 2 as the directions change. So on the real axis, you have this maximal growth and maximal decay, and then these switch over. So I'm going to call this direction the singular direction. So that's where the summation operators jump. and I'm going to call this direction the oscillating direction, and I want to avoid this bitter vitriolic debate about what we call the Stokes and the anti-Stokes directions. There are two classes of important directions, and these are the oscillating directions, and these are the singular directions. I mean, I think Stokes in his paper called them the singular directions, and had a picture of a something like, you know, the branch point of the square root of 1 minus x going towards 0. On the cover of it, it says 1857, so I stick with that. But lots of people want to change the date on Wikipedia. I don't know. It says it was read in 1857. So I spent a long time sort of thinking I was an expert on Stokes data before I read Stokes's paper. I kind of knew what to expect in there because I'd read Rames's historical description, so I wasn't surprised when I read the paper. But I was surprised that, you know, I hadn't looked at the paper. It's like if you're an expert on Shakespeare, you will have read some Shakespeare plays. Whereas if you're an expert on Stokes data, it's like it takes you 20 years to think that, you know, I'll actually read the paper, or maybe only 15. I don't know, but it's actually quite good to read. It's extremely clear. And there's a number of times afterwards he comes back to it. So for the Weber equation, you get this. You have these Stokes arrows, which basically there's a quiver description of the monogamy relation. So the off-diagonal entry can be viewed as the off-diagonal entry in the Stokes matrix can be viewed as a map along these Stokes arrows, which are at these singular directions. So I have an app which draws all of these basic examples, the symmetric Stokes diagram, but people are probably quite familiar with these from the torus knot picture. There's a class of examples I, A, colon, B. So for instance, you get the hypergeometric equation 0fq if you look at 1 over q plus 1, which I think is the GLN version of the Frenkel-Gross connection, but yeah, this version has a longer history. And so you can draw pictures. So you've got these 4 ones which are rigid. So the symplectic moduli space has dimension 0. You've got, so this is like the Bessel-Clifford equation, the area equation, the Whittaker equation, and the Hermite-Weber here. And then these two are the first, the minimally non-rigid ones. This is the one you want to deform to get Panevet 1. So the reason we have a second order equation here is because the Weil character variety for Panevet 1 has complex dimension 2, as do the symplectic leaves for the Poisson Weil character variety for like the hexagon. And then you get to these ones of higher dimension which fit into these like Panevet hierarchies. And you can describe them explicitly in terms of Euler continuance, which I think is well known. So there are lots of others. There's this atomic symbol, which is a lax pair for Panevet 4. If you look at the generic reading of the triangle, this affine A2 graph, you get a lax pair for Panevet 4 that has this Stokes diagram here. And there are others like the hyperarea equation in Bender and Orsag's book, and lots of other pictures as well. So you know, the Bessel equation is this. I've actually written out the irregular class. So it's like a rotation of the Whittaker equation that we had before. And the Bessel-Clifford is this, which is one of these minimal ones. So everything else is just sort of a pull back of that up to deformation for rank 2. Okay, so we come to this definition of a Weil-Riemann surface, which I feel someone ought to have made a lot earlier, that you know, the isomonogamy story is telling you that you get these local system of varieties when you deform the irregular class as well. You can work with the irregular type by passing to a cover, so you define a triple, so the Riemann surface with some marked points, and then you choose a rank n irregular class at each point. And then you want to look at the admissible deformations of that, just like you looked at the admissible deformation of the surface with the marked points before. So you deform the surface so it stays smooth and the points remain distinct. And there's an extra condition that we put in for the irregular class. But if you do the G version of this, this is the way that the G-braid groups occur in 2D gauge theory by deforming an irregular class. I'll hopefully get to that discussion in a moment. So the idea of like having a souped up version of a Riemann surface goes back to this Bourbaki talk of André Weil. So he wanted a definition such that the moduli space is the Teichmüller space. So he defines a surface to Teichmüller there. And if you look in the paper a bit, he also has a definition of a surface to Torelli. And I think if you read Deligne-Mumford, there's this sort of Jacobi structure which occurs there, which is some finite cover, which is smooth and doesn't have these orbifold points. And so it's the same type of idea, adding on some extra structures so you get something which behaves sort of the same. But here we're adding on a vast amount of stuff. There's the choice of an arbitrary number of Stokes circles with multiplicities. The papers actually do the versions for other groups also, which is slightly less simple to state, but nonetheless it's similar. So now we can restate this non-abelian Hodge story in this language. So we choose a rank n Weil Riemann surface and we choose some boundary data. So basically you get a moduli space, that, an algebraic or holomorphic moduli space of connections, and similarly with the Higgs picture, and we suppose that the boundary data is chosen so they aren't empty. There's a sort of an analog of the Deligne-Simpson problem which occurs. So the statement would then be that there's a hyperkähler manifold. So if you have the Hermitian metrics as well, so this is like a space of solutions, a moduli space of wild harmonic bundles, such that if you look at it in one complex structure, it becomes this moduli space of meromorphic connections, and in another complex structure, you get the moduli space of meromorphic Higgs bundle. So in particular, you can look at the case of genus 0 and get sort of lots of the classical examples of integrable systems that people looked at there. And in particular, were looked at by this Boalch and Markman as an extension of sort of Hitchin's perspective. And then there's a completeness statement. So these are infinite energy harmonic bundles, and I don't think it was known that these might have complete hyperkähler metrics as well. There's a paper of Kono where he proves completeness in the tame, strictly parabolic case, but that's the finite energy picture. There's a short paper of Nakajima afterwards which does not, but it turns out to hold in the wild picture if you have no nilpotent parts and no nilpotent parts in the residue data, and you have no strictly semi-stable points in the modulo problem. There's a list of references here. So the rotation of the eigenvalues and the weights is as in Simpson's table. I've adjusted the notation a bit, but it is equivalent to what he has. And then you add on this extra line about how the exponential factors vary as well. In particular, there's a factor of 2 in this hyperkähler rotation. Okay, so there's this paper of Kono and Nakajima. So basically, you need to have a stronger analytic package to construct these hyperkähler moduli spaces in the punctured case, and this was introduced in Bicard's thesis in the case of parabolic vector bundles, and his package was used in this paper of Kono and again in Nakajima to get the correspondence for the tame picture. And that's, of course, an strengthening of the precise bijective statement that Simpson proved in his JAMS paper in 1990. So you have like an analytic construction of the moduli spaces underlying the bijection that Simpson has there. In particular, all of the definitions of the objects are in Simpson's paper. Okay, and then there's a paper of Sabat in 1999 which did this sort of analogue of the Corlett-Donaldson results about how to get a Weil's harmonic metric from an irreducible, irregular meromorphic connection. And of course, if you go back to the case without any punches, you get back to the famous theorem of Hitchin, Donaldson, Corlett, Simpson. And of course, if you then take the Higgs field to be trivial, you get the Narasimhan and Shadri theorem, which was kind of the start of this. So I was a postdoc in Italy for 2 years, and Narasimhan had just retired in ICTP and stayed on there. So I spent 2 years having lunch with him. So I learned a lot of stuff there. But he never told me that he has this ICM talk, and in there, he has basically, I think, the imaginary part of this is the Atiyah-Bott symplectic structure. So I spent a long time sort of speaking about this, and the irregular extension of it I looked at in my thesis. And he never told me that there's this construction that he had. Yeah, so I think Goldman circulated a message that there's some obscure proceedings that Narasimhan did this, and it turns out it's actually in his ICM talk, and so I thought I would mention that here as well, that people maybe don't read ICM talks enough. Okay, so let me change tack to try to fit in with the subject of the conference slightly more. So I was a student of Hitchin, and Hitchin gave me Dubrovin's 1994 paper at the start of my thesis and said, there's a specific problem. I have a copy of the book. I didn't have the book at the time, it was the preprint. So Dubrovin was like extending some work of Chikotay and Vafa, who were counting BPS states. And they would have a Stokes matrix, and Dubrovin did things slightly differently. He's sort of complexified, so the matrix entries of the Stokes matrix did not need to be integers. But you can see that there's a message there that they're embedding this problem of counting and braiding of BPS states into this sort of pure math question of, you know, the braiding of Stokes data, or if you prefer, the definition of irregular isomonodromy that had been looked at before. So they, you know, sort of embedded this problem. So from a math perspective, if you did not understand the physics, you say, well, there's an interesting new type of sort of parallel transport which occurs. Let's try to understand that better. So you get to this sort of pure wall crossing picture where you ignore the applications and just want to understand what is irregular isomonodromy, and can we generalize it beyond the generic case for GLN that people had looked at before. So in particular, can we get lots of new non-linear sort of natural flat connections, which in particular, you know, the cases will be the flat Ehresmann connections behind the panel of A equations. So maybe everyone knows this sort of old story, but Dubrovin looks at these connections having a pole of order 2 and a pole of order 1, where V was skew symmetric and U was a diagonal matrix, the canonical coordinates on the Frobenius structure. And you take the Stokes data of that, you get this triangular matrix, and then as you do the isomonodromy deformations, you get the braiding of the Stokes data. And in particular the cases, these would be integers, which are the counts of the BPS states that Chikotay and Vafa were using to classify their 2D quantum field theories. So one of the main things that Dubrovin proves was that there's this equivalence between the Frobenius structures, this sort of generalized axioms of two-dimensional TQFTs that he had, sort of looking at the deformations as well, with basically the braid group orbits of the Stokes matrices of these differential operators, and he links this back to Chikotay and Vafa just afterwards. And then he has an example where he has this Poisson structure that looks to be new. So the thesis problem which Hitchin asked me was to try to understand this in the Laplace transform picture, you know, how to embed this moduli problem in terms of like the Schlesinger equations and what's the condition on the monodromy there. So it took me a year to sort of understand probably that Dubrovin had already understood this question, and you just get like the ONC reflections. But once you see that there's this sort of new paradigm for sort of braid group actions, you can't resist, you know, trying to see, you know, what the other braid group actions are that occur. So it's true in these simple examples, this case having a pole of order 2 and a pole of order 1, the Laplace transformation goes back to the tame picture. And Hitchin's perspective was that's the geometric picture, and the Stokes data isn't geometric. And my picture was like the opposite, that the Stokes data is pointing out that it's the tip of an iceberg, and there's lots of new stuff that there to be understood. And so here we are 20 years afterwards, and we understand it a bit better. So yeah, there's a bit of an explanation. This is actually in the notes from the course, and so we don't need to read this carefully. Yeah, so that's basically the story which I just said. Of course, irregular isomonodromy had been looked at in these papers of Garnier, Malgrange, and Jimbo and Mironeno for the generic connections before. So there's a precise question about sort of who crossed the wall. So if you look in Birkhoff's paper in 1913, he has this generic condition that basically the Stokes groups, or equivalently that the Stokes groups have to be dimension 1. And he doesn't really know what happens if they cross. This was understood, I think, in the Stokes data papers just before this, and then these guys, Jimbo, Mirano, understood how to do isomonogamy using this work on Stokes data. So I think this was first in Ueno's master's thesis, and then this became this famous paper of Jimbo Mirano in 1981, which did sort of irregular isomonogamy in genus 0 for generic connections. So the problem I set myself first of all was to just sort of rewrite that in a slightly more modular form. What are the moduli spaces precisely involved, and can we put in a symplectic structure which is preserved by the connections? So this is what I did. I generalized the Atiyah-Bott, this integral construction of a symplectic structure on the moduli spaces, and I made this connection with the work of Simpson that, hey, we're looking at some generalization of the non-abelian Gauss-Manin connection. That's, I think, the right way to think about what isomonogamy, and in particular the Panlevey equations are. The tame ones are the Gauss-Manin connection in non-abelian cohomology, and the irregular ones are a generalization of that. They're new things. So in particular, this is what prompted to write the letter to Bickard to say that, this is looking exactly like the tame picture, but no one's looked at the wild picture because people are kind of scared of irregular poles. Geometers tend to be scared of regular poles, but Bickard saw how to do this because he understood the analytic world needed. So the main pictures in this paper are this. There's an isomonogamy picture, and then there's a picture of the diagram that you want to prove that this map is symplectic, taking a connection, this space M star, to the Betti space over here, and you can factorize it through this infinite dimensional symplectic quotient. And now I suspect there are other ways to prove it as well. And in particular, we had this bijective Riemann-Hilbert-Birkhoff correspondence where you put in the connections on the non-trivial bundles as well, and you can prove a bijection, that you only have an injective map from the space M star, and you add in these extra connections, you have a bijection as well. The next thing I looked at was trying to understand the simplest example that underlied the quantum group. That if you look at this case with a pole of order 2 and a pole of order 1 that Dubrovin had, but don't put in the fact that V is skew symmetric, if you throw out that and just work with GLN, then the space of Betti data framed in a particular way is exactly this dual Poisson-Lie group. And this is the non-linear Poisson variety you're supposed to quantize to get the quantum group. And so even the simplest sort of framed Betti space is extremely interesting because there's like thousands of papers on the Drinfeld-Jimbo quantum group, which is the quantization of this Betti space. And this can be expressed by the fact that this map, so basically the space M star is just the dual of the algebra, the connections on the trivial bundle, and you get the Betti space over here. I think I now call this the dual exponential map. There's this family of Poisson maps which really just take the Stokes data of this connection having a pole of order 2 and a pole of order 1. So the next step, going quite quickly, was to understand if I could replace GLM by another reductive group. So we have quantum groups for all groups, all reductive groups, and so this says that you should be able to define Stokes data for other groups as well, and in particular the isomonogamy deformation should give actions of the G-braid groups, just like in the irregular case with a pole of order 2. If you look at it to be generic, you get this n-string braid group where n is the rank of the bundles. So that's what this paper did. This is, you can do it for other G's, so you indeed get admissible deformations where the G-braid group occurs. So as far as I can tell, this is sort of the way that G-braid groups occur in 2D gauge theory. And as part of that, you get this example where you get this sort of projection of the roots. So I think this is quite well known. There's a Wikipedia page that says the G version of isomonogamy is easy, and I spent a year and I was able to work out the Stokes data and prove this. Basically, I spent a long time with this book of Borel. So you basically project the roots. I think I have some pictures actually. Yeah. Okay. So this is from some 2014 talk on wall crossings. I haven't looked at it for a while. You look at connections which have this irregular type, which is minus a over z. So dq, the irregular part of the connection, is just a over z squared dz. And you take a to be in T-reg, and then you can look at the roots with respect to this choice of a Cartan T, and you can define the Stokes groups by projecting the roots. So you plot this projection. I gave a lot of talks about this in like 2001. I think the paper was published in 2002, but it was in the archive in 2001. So yeah, you get this definition of the Stokes groups in terms of the products of the exponentials of the roots subspaces which occur in that direction. I imagine this is familiar to a lot of the people here, so I'm not Darwin. So you can define the Stokes groups, and there's a more intrinsic picture with these, these tangential punctures as well. And then in this case, it breaks up in these half periods, so you get these unipotent radicals of Rel. So to define isomonogamy, you need to put these together, and it does not matter which way you put them together to get a full sort of Stokes. Originally it was the difference between Stokes factors and Stokes groups, but now in the general picture, it's not so clear how to sort of put them together, and you just have arbitrary sort of small products. So there's a paper of Martin Guest and Nanko Ho who made the link, and so I was really looking at all of the possible root projections, but of course there's a very famous picture of some root projections, this Coxeter projection. So if you take the E8 Frenkel-Gross connection, this is the E8 version of the hypergeometric 0FQ. So that would just have two singular directions. So you have the 8 roots and 4 lie on each half of the real axis. So there's like a bipartite coloring of the E8 diagram. And you put 4 on each. And then you do this cyclic pullback of degree 30 so that you get something which is not twisted, so it does fit into the picture we just talked about. And so the reason this is symmetric is because it's the root projection of a pullback under a degree 30 map. So you get this Coxeter projection in this way with all of the 240 roots being displayed, and you get these 60 Stokes groups of dimension 4. So that's a sort of a basic example of this sort of G Stokes business. Okay, so a long time afterwards, I went off and did some stuff with algebraic solutions to Panlevet equations, and I came back to this. So can we do isomonogamy for non-generic connections as well? Before we had the leading term to have distinct eigenvalues or to be in T-reg, do we get these local systems of Poisson varieties also in the case for an arbitrary irregular type? And this proves this for an arbitrary G. And so we get these wild character varieties. So there's a framed statement, you get a quasi-Hamiltonian H space, and this implies as part of the quasi-Hamiltonian axis, if you do the GIT reduction, that there's an algebraic Poisson structure on the quotient with the symplectic leaves by fixing the conjugacy classes on these Stokes circles, or the G analog of them. That's the first part, and then the second part is to see, again, we get the notion of admissible deformation, and you get a Poisson local system over an arbitrary admissible deformations. That's a vast generalization of the topological non-linear connections which underlies the Panlevet equations. Yeah, this was okay. And then the last paper in the sequence is paper with Daisuke, which explained the Twisted case as well. We had to sort of upgrade the language in order to see that the same two-form works also in the Twisted case as well. So in particular, we put in this picture from Aries, from Stokes's paper. I mean, it's called the Airy equation, but I think the equation is actually due to Stokes, and Airy just had the function. But this is a historical remark. Okay, so I wanted to quickly explain the TQFT picture. So I go back to the sort of the simplest example of these fission spaces. So I want to just have a look at the local picture at a pole. So I do the real oriented blow up. So I get this annulus with two boundaries. So I have like a GLN connection in the middle. So G is just GL of a vector space. And then we have this breaking of structure group. There's a graded local system near the boundary. So I've got a vector space broken up into these pieces, indexed by some set I. So here I'm looking at the untwisted case for GLN. And so H is the graded automorphisms of this. And then you have some tangential punctures, and there'll be a Stokes group for each of those. In the simplest picture, you have these full triangular groups which alternate between upper and lower triangular. And then you can define this wild surface groupoid. You would choose a base point on each of the boundary and define this groupoid, so all of the paths in here. So basically I'm trying to sort of define an object which captures the topological objects which occur. So I have a local system of solutions in the interior, and there's a graded local system near the boundary which gives the formal classification, and then the Stokes picture or the multi-summation picture gives you a way to glue these. And so that's the gluing here. And so on the singular directions it jumps, and so you have to have this tangential puncture or something equivalent. And so the Stokes matrices will be the monodromy around these tangential punctures in this picture. But you know, we have precise axioms, and we know how to classify connections in this way. And so you have a definition of a Stokes local system, and you classify by defining this groupoid. And if you choose certain paths, you can describe this quite explicitly. So for instance, it's G cross H cross the product of the Stokes groups. So G would be the connection matrix here, and H is the monodromy around the graded boundary, and these will be the Stokes matrices. This should be familiar from particular examples. So it's just the isomorphism classes of framed Stokes local systems. And the statement that we prove is that this is a quasi-Hamiltonian G cross H space. So people have developed various extremely nice ways to construct the character of a variety algebraically. And we use the language of Alexeyev, Malkin, and Weinbrenken, or the complexification of it, in order to get these spaces as well. So let me just go through their story.
Could you just go one? So here, this is just the ordinary fundamental group.
Of this surface with these tangential punctures, yeah. So that would give you Hom pi G, but you need to put in these Stokes conditions as well, that says that it has to be in H if you go around the boundary, and the monodromy around these tangential punctures has to be in the corresponding Stokes groups. So you're not looking at all of the representations, you're looking at the Stokes representations of that, and that has this magical property that it will be Poisson as before.
But it sounded like holonomic conditions that you were just saying. But it's not quite that, or is it?
The exact condition is that the monodromy around the tangential puncture has to be in the Stokes group. So I'll have a picture with the quivers in a moment, and you have these like Stokes arrows, and those are parameterizing the possible off-diagonal entries. And I'm sure that's just a translation of something that Ekal has in terms of alien derivatives or whatever. But the fact is, you can write down what it is, and you can do the G version of it and define Hom S pi G as a affine variety with an action of this, the groups H. And so part of this is that the moment map takes values in G cross H. That is the monodromy around the boundary. It's just here, it's in H because I've got this reduction of structure group. The reason I call them the fission spaces is because it's a natural way to break the structure group from G to H. Eventually we want to break these off and glue in different ways, but I don't know if I'll get there before the end of the talk. So the standard Alexeyev, Malkin, Weinbrenken picture of this is perhaps the fifth sort of algebraic construction. I basically read all of the different ways to do it and found the one which I understood the proof of and generalized that to the Weil picture. I mean, understood the proof of as a graduate student. I may understand more now, I don't know. So they look at surfaces with one boundary component and look at the framed connections there. So there's still this action of G changing the framing, and they cook up this analog of the symplectic 2 form and a theory of group valued moment maps, so that the moment map is the monodromy around the boundary using the framing. So in particular, this product of multiplicative commutators is a basic example, and they get to this with this fusion picture by chopping it up into these pairs of pants. So their theory implies, or the complexification of their theory implies, that you get these Poisson structures from the quasi-Hamiltonian two forms, with the symplectic leaves being the conjugacy classes of monogamy, eventually in H, or the twisted version of H in the Weil picture. So this should be familiar, and they get this. They construct these by fusing. There's this fusion operation, which is just the product. So you just need to construct the case with one handle, the internally fused double. So you have this toolbox of pieces. You have like the one punctured sphere, the cylinder, and the conjugacy classes to reduce that, and you fuse and reduce, and you get all of the tame character varieties of Riemann surfaces of algebraic type. So all of the spaces they get are of this form, and we're pointing out that there's a vast number of new spaces because we have these new pieces we can stick in the toolbox, these fission spaces. In particular, we can break the group from G to H, and then glue on an H surface and then pass to something else. So in particular, we wanted to construct the Betty data of connections, but we got a lot more because we get all these things with the varying groups, which I now call the fission varieties. So I adopted this name in the second paper, which is in 2009. So this is my sort of attempt at a generalization of the Weil non-abelian Hodge picture, just to ask, are these spaces hypercalar as well? This should be some type of vast extension of the spaces that we know. This is written as a conjecture in this paper in 2009 for Malgrange's birthday or something. So in particular, it's possible to do things like this. You start out with GLA plus B, and you break it up into these two pieces, some block diagonal group. You take three of these and you can glue together. The theorem is that that will have an algebraic symplectic structure. And so can we put a hypercalar metric on those? I think we can, but I don't know if many people are aware of this question. But, okay, and then you can go back and look at particular examples. These are the type of wild monogamy relations in Birkhoff's paper in 1913. This is in Jimbo Mironeno's paper, the first sort of example of such a relation which I saw. And if you see that and you know the tame picture, you're just sort of crying out to find the quasi-Hamiltonian two form such that the left-hand side here is the wild monogamy relation, that you have a group-valued moment map interpretation of these relations as well. So in this generic picture, this was in this paper on the archive in 2002, and there was this C infinity picture slightly earlier. And then the question was to extend it to non-abelian ends and the twisted cases as well. And this sort of converged in this paper with Daisuke in 2015, where we sort of have arbitrary twists, and we've even got local systems of groups in the interior, which I don't. So Renken posted a paper 2 days after we put it on the archive that he did these twists as well for compact groups as well, but I hadn't realized it was so competitive. Okay, and then you can look at certain examples and you get back to these, the quasi-classical version of the quantum group if you have this pole of order 2. So the Drinfeld-Jimbo quantum group, it is modular in the sense it's something to do with the Betty spaces for irregular connections on curves. And you can look at the case with the block diagrams. We had G and T before. Here's G and H, and these are exactly the Laplace transformations of the logarithmic, well, the representations of the fundamental group of a punctured sphere. That there's an on-the-nose isomorphism between the ones that occur in these cases of a pole of order 2 and a pole of order 1, and all of the tame character varieties in genus 0. This is basically what the Fourier Laplace transformation does, and it was computed in chapter 12 of Malgrange's book in this generality. But Dubrovin and people had understood a paper of Balsa, Jerkas and Lutz, which did it in the generic case that was enough to do the question that Hitchin asked in 1994 or so. So you get to this sort of Torelli type question: what are the representations of the moduli spaces? So the work I've been looking at more recently is more to try to classify the different representations representations of the spaces. Here we have two spaces which are isomorphic, and it either can be realized as a space of representations of the fundamental group, or as this irregular picture having a pole of order 2. And we would like to know what are all of the different sort of possible representations of these spaces. We also have an example where this Frick-Klein-Vott space related to Panleve 6 occurs for the G2 character variety. There's a paper with Paluba that looks at that. So even changing the group does interesting examples as well. Okay, so then there would be a story about how to get the graphs. There's a basically, geometrically speaking, Plato had the Platonic solids, and then the next most interesting geometric things basically are the Panleve equations and their rich structure. And you can try to classify those in terms of diagrams as well. And you sort of end up with, there's a class of graphs which occur. So the non-abelian Hodge graphs, and for each of these we can define this whole story with the 3 algebraic structures and the deformations. So for instance, Panleve 6 would be the one to do with affine D4 for the standard sort of imaginary dimension vector. But there's lots of others. Basically an arbitrary complete k-parsite graph would work. And once you get to higher order poles, you start to get double and triple edges as well. And we understood recently how to read this off from the Stokes diagram. So let me just give this an example. So for Panleve 2, you know from Okamoto you should get affine A1. So you draw the Stokes diagram like this, and this would have these Stokes arrows. And then you see that the monodromy relation really is a representation of this quiver. So the formal monodromy is a local system on these Stokes circles, and so you can draw it in this slightly different way. And then the Stokes data basically involves maps along the arrows, so you can pull it apart and get this picture here where you have these alternating arrows. So you would get a quiver like this, and then there's the monodromy relations, so you need to subtract off the relations that come from the matrix entry. So if you subtract off this from this, you indeed get affine A1, which is the graph we expected from Okamoto, but now this works for an arbitrary connection on P1. And so we can define the graphs in general. So for instance, for area equation, we get A1, we just get the point, which reflects the fact that it's rigid. So the moduli space is dimension 0. And for Panleve A1, we get affine A0. And you can draw the picture in this sort of fission way, like this as well. So I'll stop there, and I'm sorry I'm over time. Thanks.
Questions?
Little comment, yeah. Yeah, you at some point you have this A, B, you try to group 3 irregular things to get something else. And there is a language probably knows this singular Lagrangian submanifolds, and there is local Foucault categories associated to them, and then you get like singular surface in 4-dimensional symplectic manifold, and then it's produced plenty of these Gaussian varieties. So
right, it would be interesting to see if it matches up. I mean, it's
and in order to get hypercalorimetric, in general, with Jan we have a picture, we have Poisson surface.
Right.
Yeah, and then things should come up.
Is this a proof, or is it an idea of a proof? Or is that
The claim, yeah.
Yeah. Well, I have a claim as well. My claim was from 2009. But yeah, I think there is something there, and there should be a rich class of new things, and so it's
it's a claim which agrees with known examples.
Right. I think the multiplicative quiver variety people, I mean, those examples are a special case of this, that this Vandenberg edge occurs for this non-abelian Hermite-Weber equation or something, this disk with the 4 directions. Okay.
Yeah. I just wondered how much of this is sort of, or if any of it is known, how to quantize these pictures. How can you quantize these moduli spaces? Is there any work done on this?
Well, Gabriele did this work, but that was more the de Rham side, trying to get the irregular Hitchin connection. And we tried to involve you, but it was sort of a bit tricky to get you to focus. Yeah, there is a link with this cluster business that I'm not entirely comfortable to say sort of what the intersection is, but there's certainly, you know, an intersection there, and I'd like to understand better what it is. I mean, I've looked at a number of the papers and there's loads of different definitions, whereas here we just have this monogamy relation. You have a clear definition of what the space is. And so I think a lot of what they do in certain examples could be better understood in this very precise Weil non-abelian Hodge picture.
There is a theorem that all Weil character varieties are cluster Poisson varieties. Therefore, it implies that
No, there's a paper with that statement. I think there are two papers, but they don't contain a precise statement, and we need a definition and theorems with actual capital T's. I haven't seen a clear statement. I've heard the words, I've looked at the papers, but I think there's a basic issue with papers not having precise statements in. It's not as simple as that.
But there's also, I mean, two different kinds of quantizations we're talking about, right?
Sure. There's the de Rham side, the Betti side, the open part.
To form the you know, multiplication of the functions, but another one is to actually somehow get a vector space, get operators acting. Right.
So, I mean, Gabrieli does have these generalizations of KZ in certain examples, I think, with poles of order 3. But how to interpret sort of what they mean, and then we would like to make the relation with, you know, the physics people. But there's definitely, you know, flat quantum connections which are there. Yeah, it seems to me that there's this vast sort of amount of stuff which sort of needs to be organized better.
Well, I guess this is, I mean, forget about the Weil case, this is also even a problem in the Tame case.
Sure. So, okay.
No questions? If there are no questions, thanks again.